This is my last technical talk. I have one more talk tomorrow, but that will be some general talk about where we go from here further. Most of the images you have seen so far have been grayscale images. Only the retinal fundus images had color, but our processing was using only the Y channel, the luminance channel. So we didn't use the color information. In that case, although it is a full color image, natural color image, the blood vessels have high contrast only in the green channel or the Y or the luminance channel. So only those two channels have been used. Red is noisy, blue is noisy, so they're not used. Just for blood vessel detection. If you want to detect hemorrhages, it may be useful to use the red channel. Now, after writing the two books on biomedical signal analysis and biomedical image analysis, my attention turned to color image processing. By that time, I had worked on a few color image processing projects with my collaborators in Romania, Dr. Mihaichuk and his professor Vasile Buzuloiu, and also in Spain with Begonia Acha and Carmen Serrano. So then we had a few papers, not a whole lot of papers, but we had looked into some aspects of processing or analyzing color images. We had encountered a few applications of color image processing. And also in Brazil, I worked with dermatology images, and they also, color is important. So then we said, okay, let's put all these together and see what we can do, and to address the basics of color image processing. At that time, when we started working on this book, there were not many textbooks available on color image processing. There were a few compiled books on color image processing with various applications, but most of the books were more on color imaging and color representation, sensors, printers, and such, not on analysis. Some of the classical textbooks on digital image processing had small sections on color image processing, and they have expanded in new editions. But at that time, the color image processing sections in standard digital image processing books were fairly small and did not go into much detail and did not have much in terms of illustrations. Dr. Venetsinopoulos from Toronto, University of Toronto, has a textbook. It's still there, Vitas and Venetsinopoulos, and that's perhaps the first textbook on color image processing. But it lacked illustrations. The fundamentals were there. There were some illustrations, but we wanted to prepare a textbook with more illustrations that could easily and clearly convey some of the notions of color image representation, capture, and add some applications of image processing. At first, we had a big plan, but then we ran out of time and the size of the book and all that. So this is a small book. One of the colleagues of Begonia and Carmen, Jose, is our fourth co-author. We are working on the second edition, which will be expanded compared to the first edition. So again, I would say, don't buy this book. Wait for the next edition, but it may take 2 years. We are working on it. So Begonia Acha and Carmen Serrano are with the University of Sevilla in Spain, and they have visited Calgary many times, and we have worked on various projects, and I have been there a few times. So this is a collaborative project between the University of Calgary and the Universidad de Sevilla in Spain. Now that's the cover of our book, showing retinal fundus images, the original color image and its red, green, and blue components, and the color circle that I'll explain as we go along. So first, let's look at the nature of color images. What are color images? What is color? And how do we represent? Where do we encounter color? Where is it important? In Canada, sometimes we get double rainbows, even triple rainbows I have seen. And interestingly, the second rainbow has the colors in the reverse order. And then I have seen multiple such patterns. I got this from Chris Pollock, who is a famous photographer, in the Kananaskis Mountains, very close to Calgary. 75 kilometers from Calgary, we have a beautiful provincial park. where we go for hiking. So the color spectrum is this, where out of the total spectrum that we get from the sun, there is a very small portion, 380 to 750 nanometers, that our visual system can perceive. And some people may not be sensitive to certain parts of the spectrum. They may have different sensitivity or limited sensitivity. Some animals may have a bit more into these ranges beyond the red and into UV. So it depends upon the biological system, and there could be some variations between people in the sensitivity and reception of this range. But it's a very narrow range compared to the total range, going from low frequency radio waves to very high frequency, going beyond ultraviolet into cosmic rays. We're not sensitive to those. What are the important color attributes? The most important is hue, that is the dominant wavelength or band in the spectrum. So we're not talking about one frequency, but a band. Saturation, what is the quality or colorfulness of that color? Is that pure red, or is it diluted with white, sort of rose pink and light pink and so on? Intensity of brightness, but that is not color. So these are the chromatic components, chrominance components, and this is just the non-chromatic, or just the intensity part. So intensity brightness, that is what we call grayscale. I don't know why it is called grayscale. It should be a brightness scale. Gray means dark. So 255 in gray should be dark, but it's reversed. Chroma and lightness and a few other terms are used in the literature, but these are perhaps most commonly used. So the HSI system, or HSV sometimes is called value. HSI is perhaps the most common representation, where hue and saturation represent the actual color components, and intensity is just the brightness part, no color. The human visual system has rods that are sensitive to light intensity only. And so we can see in a dark room also, but we don't perceive color. If we turn off all the lights, not turn off all the lights, but keep a little bit of light, we can still see you, but we won't be able to differentiate between colors. So the cones that are sensitive to light work at a slightly higher light level. We need some minimum amount of light for the cones to work, and they are sensitive to red, green, and blue. Not just RGB, but bands like this. So they're called long, medium, and short cones, LMS. L is sensitive to red, but it's a big band. Okay. The peak is somewhere in the red area. That is the green, and this is the blue. So with reference to the peaks, you are in the RGB range, but they're sensitive and to a broad band, and they do overlap. There are a number of representations of color for imaging, image processing, image printing, and so on. The most common is RGB, red, green, and blue. It is assumed that all colors may be represented by some linear combination of RGB, which may not be true, but that is commonly done. And then CMYK, cyan, magenta, yellow, and black for printing purposes. Now, black is added only to minimize the use of all these colors. If you combine CMY, you get black, but why throw that much ink? You're wasting ink to get black, so black is added. You could add white here if you want and call it RGBW, but that is not commonly done. This is for light, and this is for dyes in printing. So this could be called the additive primaries, and this could be called the subtractive primaries or secondary primaries. HSI, as I mentioned, and then there are some standardized representations from the International Commission for Light. CIE is the French name for the International Commission for Light, and some committees have come up with standardized representations to improve the representation of color and bring certain measures of color closer to human visual perception, such that some attributes and distance measures computed in these domains match or agree with human visual perception. RGB may not agree with human perception when you compute measures and differences. And then there are these others, YIQ, YUV, and so on, that have been used for various other representations of color signals in TV and other applications. CIE also came up with standardized RGB in XYZ coordinates. I'll mention some of them, not all of them. So here we have what are called color matching functions. Given an arbitrary color, can you represent that in terms of coordinates in some space? Like using basis functions. We have seen wavelets, Fourier transforms. So here we have color matching functions defined in the wavelength spectral domain. Wavelength, or take the inverse, you get frequency. So this is essentially the spectrum related to red, green, and blue, but these are what are called color matching functions. So when you take the projection of a given arbitrary color spectrum that has a combination of RGB, you project onto this, you get the blue component, and project to that green, project to that red, but then the red has been defined with some negative values. Of course, there is no negative light, but that function has been defined with negative values. And that has been changed in this to be all positive. So these are color matching functions in the XYZ domain. So now you take the projections onto these XYZ functions, spectral functions. Take projections of the spectrum of your color signal. And then you get the XYZ components, like the Fourier coefficients or DCT, whatever. Okay? Projection is the dot product or point-by-point product and addition of your spectrum with one of these. You get the corresponding component. Then you represent the arbitrary color in terms of these XYZ coordinates, and if you normalize by dividing by x plus y plus z, then z is 1 minus x minus y. You only need 2. You don't need 3 after normalization. So there is this CIE, so Commission Internationale d'Éclairage is that CIE, International Commission for Light. So this is a domain or a space that is defined with red, orange, yellow, green, cyan, blue, violet. And this could be the gamut of some device or sensor. Not all devices and sensors and visual systems may occupy this whole range. So this is of somebody, something. And there is a reference light given D65. Some illumination source is specified. So this is the XY plane. X coordinate, Y coordinate, with projections with respect to those functions, like the color matching functions, normalized by x plus y plus z. So z is not required because it is 1 minus x minus y. So now the 3D variable is displayed on a 2D grid, if you want to call it, or space. And within this range, you can display or show the gamuts or the operating range of different devices and systems. So you can give the coordinates of a color representation in this manner using RGB that are mutually orthogonal in some sense, or cyan, magenta, yellow, and black is at the origin, white is there. So you have this color cube now. So an arbitrary color will be a point somewhere inside, depending upon which system you use. And RGB and CMY are complementary in this sense. Now it is better perhaps to represent using the dual cone model here, where HSI values are used. Here, intensity is this vertical axis going black to white. When there is no light, you can't see color. So no point in showing this. You could also show this as a cylinder if you want. but we don't perceive color here. Similarly, when there is the highest amount of light, we don't perceive color. So color exists or is perceived somewhere in the middle for a certain range, and on both sides, color perception vanishes. So that is intensity. Hue is the angle in the circle. Saturation is the radial distance within that circle. So hue typically is represented with red at 0, yellow, green, cyan, blue, magenta. And then a point here will be red, but not pure red. If you want pure red, you are there on the circle. If you come closer to 0, the center of this axis, then red becomes lower and lower shades of pink, lighter and lighter shades of pink. Similarly, green and other things. Okay, so this is HSI. So to show in pictures, I like to show these as pictures. So I spent some time in MATLAB playing around, and I was happy when some nice pictures came out. Some of these are obvious, but until they are shown, they are not obvious perhaps. So if varying hue with constant saturation and intensity, so there is no saturation variable here. So the same color comes right through, but the color is red here and slowly moving towards yellow and green and cyan, blue and magenta, and then merging back to red. So it is periodic if you want to go around. So you only go 0 to 360 for 360, not 180 for hue. And there are these diametrically opposite colors. So this is a vector space. So if you have a red vector and a cyan vector and add them, you get 0, right? So that way. And the separation red to green is 120 degrees. Green to blue is 120. Blue back to red is 120. And cyan, magenta, yellow are similarly placed. Now, if you include saturation variability, then from here, as you go to that is pure red and various shades of pink. And the color gets lighter and lighter as you come close to the origin. So this axis is saturation axis. Okay? So that is Begonia and that is Carmen, and we have worked together for a few years, more than 20 years. So we said, well, let's have some fun, and got RGB, and that's the red component. Where you have red, the values are high. Blue have nothing, so my blue component is 0, and for her the green component is, and so on. Obvious. So this is red plus green plus blue. So if you add them together, you will get that. Now, how do you represent this information of a digital image? We take the histogram of a grayscale image of the number of counts of each gray level. Now we have multiple possibilities: red, green, blue, intensity, and so on. So the black line is grayscale. The red is the red histogram. There is a large peak, that is my shirt. And there are some low values of red. Sevilla is very hot in the summer, hot and dry. 45 degrees, you can't even touch the car door handles, 45 and more. And the streets in the downtown area are very narrow. That's the way they designed it in the olden days, so to prevent attackers from coming in with big vehicles or large numbers. But everybody has the AC unit facing that way, so you cannot even walk in these narrow corridors because all the AC units are blasting hot air out. It's already hot. So we got a little roasted, I suppose. So there is some red there too, and that wall there has a combination. So there are some low levels of red that are not so obvious, and the others green and blue. So that's one of the blue shirts, that's one of the green tops, I suppose. We can also plot in 3D. Shantanu Bonik, my PhD student, developed this program. I had seen this in some of the books. So it's a 3D plot of the occurrence of various colors in the RGB cube. So the intensity of this represents, the value of that represents how many pixels of that value of red or that and so on. So the yellow part is here, the red is somewhere here, the green, all that is there, the cyan or blue, it's there, and so on. You can perform 3D segmentation in this space. HSI, if you compute the hue angle and saturation and intensity, these are the components. But there is a problem with hue, for red especially. You get red here, 0 degrees. 1 degree is red, but 360, 359 is also red. So if it jumps between 0, 1, and 359, you are jumping across a large range. So the red here, my shirt, has all these very bright values for 359 degrees and very low values for 0, 1 degree and so on. That's a discontinuity in the representation of hue. For the other blue and green, it's not a problem. Okay, saturation, my shirt is pure red, that is not pure green. That blue perhaps is close to pure blue. If you take the sine of hue divided by 2, then that becomes distance from red. So don't display the angle as such, take the sine, and then those things are cleaned up. So what is the distance from red? So positive or negative, 1 degree this way or 1 degree that way is the same distance from red. And you can then display sine of hue over 2. Sine of hue of 120 divided by 2 is distance from green. So this is green, so the distance is 0. And red and blue are equidistant from green. So these two regions have the same distance. So you can take a distance measure and then analyze color with reference to some color. Then you can overcome some of these limitations of representation of hue in angle. So if you want only the color information, the chrominance component, take the luminance away, then in the HSI system, you want just hue and saturation. So there are only 2 variables for color. So now you can plot the histogram within this ring, going from red and so on, I mentioned earlier. So my red shirt is there with high saturation. And that perhaps is the wall, sort of between yellow and some sort of brown. And, or maybe this, sorry. Now this would be that wall. And the green top is there and the blue top is here. So now we can perform segmentation of color only, throw the intensity out in 2D, in a 2D space. So if you play around with hue, saturation, and intensity, you can get a few different types of pictures. Here I have kept the hue component with maximum saturation and intensity. So this green is not the real green. Green is that. Sometimes I get confused. No, that looks green. No, but green is that. Similarly, blue is that. There. Maximum saturation. Whatever that color is, saturated rather. This is iso intensity rendition with original hue and saturation. The intensity is maximum. And the original values of the saturation, yeah. And the last one is just the intensity component, grayscale. So in this way, you can extract different types of images depending upon which part is of interest: intensity, hue, saturation. And then you can separate chromatic and achromatic or non-chromatic pixels. In this image, which pixels have no color? Nearly black, nearly white. So close to the saturation being 0, go there and take those pixels. Put a condition that regardless of the hue angle, saturation must be less than something. Whatever cutoff, 0.1, 0.2, something. And then if the intensity is also below a certain threshold, you get black pixels. If the intensity is above some threshold, you get the white pixels. There's a little bit of color, so the saturation is not 0. I load up to 0.1 or I don't have that number, some threshold. If I put all of them together, I get the non-chromatic pixels, pixels with almost no color. Then there is the question about natural versus pseudo color. So I put a number of pictures, took a number of pictures. The machine lab in our department, RGB used there. Here Y is used in India for one of the phases. There it is RGB, and depends on the country. That color code, there is black here for ground, and so on. So you use that just to connect properly the phases. That's just convention. So that is color coding. And this is for artistic representation. The color represents the nature of that character in the play, and just to make it more attractive. In pathology, stains are applied. The color is not a natural color. It depends upon the stain that you put and how many stains and how they interact. And certain parts of the tissue will take up certain stains, others will take other stains. So they get colored differently, but that is not natural color. You can call it color coding or pseudo coloring, both. But perhaps more accurately, it is color coding, because the color tells the pathologist what that represents. There is a code there. Or some toys for visual matching of objects for babies and children to learn about color. Retinal image, this is natural. The palettes, that is natural. In retinal images also, color can play important roles when there are exudates that are bright, not necessarily always white, yellowish. And there could be some greenish pigment deposits. Red represents hemorrhage, and blood vessels are here. The optic nerve head area is also typically bright, yellow, not really white, sort of yellow to white. So color has some meaning here. In the normal case, color doesn't play an important role. Although we see the blood vessels as being sort of red, the contrast between the vessels and the background, which is also sort of reddish, is the best in the green channel, not the red channel. And there is no blue in most of our body, unless you get hit and there is a bruise that could appear to be blue. But there is some green in somehow, in some places. Just a pigment. Maybe that's some combination. In medical imaging, when you fuse multimodal medical images, in this case MR and PET, I think, you have one image here, that is MR, this is PET showing some increased activity there. And when you fuse, you can include the anatomical information with the physiological information or functional. This is purely anatomy. This shows the anatomy, but not in high resolution, but it shows the uptake of some radiopharmaceutical that is put into the patient, injected to the patient. So this is functional imaging. So it depends upon how that part of the body is functioning. If there is a tumor, it takes more blood supply, hence it's of a higher intensity. Put them together, you can interpret this functional image in the context of the anatomy. And their color is important. Even here, this is pseudo color, it doesn't matter. You can show it in any color you want, but it was given red color, and you put them together, this shows up in red on top of the grayscale image. You could put it in green if you like. So it doesn't matter, but it is pseudo coloring. In early days of computer tomography, because of the large dynamic range of -1000 to 1000, to display on ordinary CT, ordinary computer monitors, which used to be video devices at that time, it was felt that, or some recommended that, well, why don't you go to color? Because the human visual system, at a given level of adaptation to light and how much your pupil has opened, you can perceive perhaps a few tenths of gray levels, maybe 20, 30 gray levels, that's all. But we can adapt. We can window. I can see details here at various light levels, but I have to wait for my people to adjust to that lighting. And we can go outside. I can still perceive you as you. So what matters is the difference. As I mentioned, the human visual system is a bandpass system. The absolute intensity doesn't matter. I can see you with a little bit light and recognize you, and also out in the sunlight. But we can perceive more shades of color, hue, saturation, and so on, with intensity. So it was felt in the early days of CT imaging that because of the large dynamic range of CT images, it would be better to map them to some color. But it's only one value per pixel. So one value, turn one value to three values of RGB, you get some fancy colors, and yeah, you can see some details, but they are totally out in the sense it doesn't look like the original CT image. So those methods of pseudo coloring failed. Radiologists were not impressed. Computer scientists perhaps thought it was cool, but radiologists did not really catch on to that. They were happy with just shifting the window of the Hounsfield unit values and looking at low density tissue, soft tissue, hard tissue, bone, and so on separately. So it is important to recognize here that our system can recognize and distinguish between only a few tenths of gray levels right now, for me, in this setting. Turn down the light level, and my pupil will open up a little bit more. Then I can see all of you again in a very similar manner, but we have shifted in the range of the grayscale. But it takes some adaptation. And again, as I said, we go outside, bright light, we can see. But if you come from bright light suddenly to low light level, we are sort of blinded for a little while. We can't see anything. Similarly, after adaptation to this, you suddenly go outside, you can't see anything. And it takes a little while for this change to occur. Whereas color, we can see more. But color can be seen only when there is adequate light. Acquisition of color images. A sensor with color filter array data. So we don't have separate sensors for RGB in most cases. An intensity detector is used with a filter to capture in one shot. If you want, you can have different sensors for RGB, but then it takes time. And we won't stay still, we will move, and the picture is ruined. So one sensor of light, put filters. You can put 3 filters and take RGB separately, but that takes time too. So instead, there is a color filter array. You need dark current correction because the CCD elements have some noise. So even when there is no light, when the lens cap is on, there will be some electrons jumping around due to thermal energy, and there will be some dark current you have to correct for that. White balance. The color we perceive depends upon the spectrum of the light. There could be some bluish tinge here. If I stand here, I don't have any color, so it doesn't matter. But those of you who have gone shopping for clothing material, especially saris, know that the color of the material, the sari, let's say, I like sari shopping too. We went sari shopping, but the color changes with the light, whether it is fluorescent light or it used to be incandescent, but nowadays LED. LED could give you anything. Previously, LEDs only gave one particular band of light. Nowadays, they give you a different spectrum. And that light will affect the way you perceive. The spectrum of the light is reflected from the object. And if the spectrum is not uniform, what you perceive is not the true color. The same we saw with any projection. The received image is the product of the reflectivity of the object with the illuminating function, light. If the light is not uniform, you're not getting my picture, it is some distorted picture. Similarly for color, the spectrum of color. So it is common, I don't know if you still do it, look at the sari in the light in the shop and then say, well, I want to check the color outside. Come outside, check in sunlight, and then in Bangalore, the salesperson Many of them are men there. So they would even wrap the sari around them and show with pleating and everything. And then you tell the guy, well, this is fluorescent light, come outside, I want to see you in sunlight. So the guy with the sari has to go outside too. Anyway, that is white balance. You have to correct for that. Demosaicing, I'll show you that. The mosaic of the color filter array. Color transformation to unrendered color space and color transformation to rendered color space. So demosaicing is interpolation to get the other color components from a single pixel of the received array, which will have only one color component because of the filter that is put on your CCD detector. The CCD detector just detects intensity. There is a filter on top with RGB. So under element 3, you only get the CCD under that will give you the red component, that will give you the green, and those will give you blue. So to get the other components, to get the green and blue components for number 3, then there are some demosaicing algorithms that say, this is one of them, that says get the horizontal gradient, delta H is G2 minus G4. Get the vertical G1 minus G5. And if delta H is more than delta V, you come here and average these. G1 plus G5 over 2. And G3, that goes to number 3. And if delta H is less than delta V, average 2 and 4. So G3 gets G2 plus G4. Otherwise, you average all 4. Green. The blue will be in the corners. So do the same for the blue. So instead of just averaging all the 4 green, all the 4 blue data in the neighboring pixels in the 3 by 3 block, you take combinations of 2 or 4 depending upon the vertical or horizontal gradient. So you don't blur across edges. That's the idea. So this pixel will only get the red value from the original sensor data. The blue and green components for that are estimated in this manner. And the same for the others. So these are some of these charts that have been prepared, or this is one of the charts prepared, called the Macbeth color checker. And when you image this using different light sources, you get different colors. So the colors are the same. It's a printed piece of something on paper or some material. And that's like a test pattern, let's say a phantom image. And the values, the RGB values for each of those patches is given by the manufacturer, standard, in XYZ or RGB. So this is using what is called a xenon flash. This is fluorescent light. This is diffuse sunlight. So much difference, and that's why you want the sari out in the sunlight, assuming that to be the true color. So there is substantial variation. So you have to correct for that. If you have this color checker, then you say, okay, this is supposed to be that color, but I'm getting that color, so do some correction for that. So that is color calibration. Oh, I'm supposed to give you an image alert, and some said, well, don't show me these pictures without telling me first. If you don't like it, close your eyes. So Begonia and Carmen worked on teledermatology, where in some primary healthcare center, if a person has some sort of a lesion, in this case due to burn, it has to be diagnosed immediately and some treatment has to be applied immediately, but specialists are always in cities, radiologists, dermatologists, whatever. So you need to send those pictures by some sort of data transmission. But then the calibration of the color is important. So here, this was taken with a xenon flash using Canon camera, B's Sony camera. Now, there is a difference in the magnification, but the colors are slightly different. There is a bit of a magenta here, which is not there. After calibration, what is called characterization, these are the images where they are almost the same in color except for the scale. The color difference here has been reduced. So you could say this is the correct color. Filtering you have seen. So let me talk about some filters for color images. Neighborhood shapes you have seen. Mean and median filter you have seen. So we'll just skip all of that. Now, in the case of scalar pixel values, each pixel has one value. So doing this is easy. In the case of vectors, taking the mean is not a problem. You can add vectors. These are the RGB pixel values in a 3x3 neighborhood of a color image, actual values. In all my examples, I like to have actual values. I can make up some numbers, but I try to give real data. So these are real pixels extracted from some image. This is the center pixel and the 3x3 neighborhood. So each pixel now has three values, RGB or whatever else you have converted it to. RGB you can average easily, just R plus, add all the R components, divide by 9 and so on. So that is not a problem. But median is a problem. How do you sort a vector with three components? Because you want to get the median, which is the middle of that ordered list from minimum to maximum. So marginal median was suggested initially. They said, well, take one of the components and sort by that, red only. And take the green and sort, and take the blue and sort. But now these, if you do that, these colors did not exist in the original image. You get some other color. Take the median and it is something, some value of that. This is called marginal, but then you're creating a new color. All these are values that did not exist in the original image. Perhaps some existed somewhere else, who knows. Reduced ordering says, compute some measure rather than the actual pixel values. Use something as a reference and compare each of these pixels in that neighborhood with that reference. Compute a distance. The simplest is Euclidean distance to the mean. X bar is a mean of those 9 pixels. And take xi minus x bar, transpose xi minus x bar, or component-wise difference square and add over all the components. And these are the distances. Now you rank order by distance to the mean. Now this quantity is a scalar. Rank ordering is not a problem. So you're not rank ordering the actual RGB values directly, but instead you are computing some function with reference to something. And here it is Euclidean distance. So some will say, well, Euclidean distance in RGB is not good. So okay, go to LUV, LAB, whatever you like, and do that. Okay, so that is the mean value, mean of all these RGB values. Take the distance, and these are the distances truncated to just integers, rank order. Now, here you don't go to the middle, you take the first one, that is the closest to the mean. You take that. Now there are other distances, vector median and vector directional. The sum of distances from each vector to all other vectors, di. And then this d is Euclidean distance from xi to xk. And that the sum of all that. So how far are all these pixels in the neighborhood separated? Use that as a reference. And take the one closest to that. That has a minimum distance, rather. The distance could also be in terms of angle, color, throw intensity out, and take the angle, which is given by the dot product normalized and cosine inverse. So for each pixel in the neighborhood, you compute the angle. So different measures to convert the three-dimensional vector to a scalar and use that information to make your decision as to how you want to rank order and which one you want to select for the output. So there are a number of these filters in the literature from the Toronto group, Dr. Venetsinopoulos group, and many others, modified and so on. So we took our adaptive neighborhood method that I described earlier. For every pixel, we grow a region, adaptive region of any size and shape, depending upon what is present at that location. So we get a certain population of pixels belonging to the same object without crossing boundaries. We don't want to blur across boundaries of objects. How many pixels do you want? You may put a limit. You may say 50 pixels will be enough because I'm just averaging them, or 100, or how many ever. But now the region is adaptive, like this. So this is an edge in an actual image. I don't remember which one. That is the seed pixel. From that seed pixel, this is the noisy image, a lot of noise. That became this due to noise. And that is the initial region grown. There are a number of pixels within the region that were not captured because of the region growing criteria. Mihai Chuk said, well, we should include some of them because we don't want only those pixels that are exactly similar to the seed. For averaging, we need a certain population of pixels around that in this space. So then you check for these connected pixels that are within the region and put some additional condition and include them. And the white region now is the adaptive region. There are still a few pixels that are not included because they differ by substantial amounts compared to the seed. So that is the region. And when you average this, you get a clean pixel value. And when you do that for this image, that is the output. So the effect of noise, you see all these other colors, has been suppressed. The edge has not been blurred substantially. This is zoomed into a small region. I think it's this Pepper's image. So we have many different filtered versions. I would ask you to look at these images and judge which one is the best. We have, in our papers, we have the tables of various measures. I won't go into all of those details. We did this with various types of noise. This is with Gaussian additive noise. These two are the same. There are two different images in the book. But this is, C is the MMF, the mean filter, and vector median, and distance, DDF, GVDF, and so on. And ours is where? Ours is the last, of course, and this is the adaptive neighborhood filter. So you could compare this. There are so many other filters. I have not gone into those details. This is just a very broad overview, like an introduction to color image processing. So I'm not going to describe all of these other modified distance filters. We have described them in the book and also in this paper in SPIE, Journal of Digital Imaging, Journal of Electronic Imaging. So we showed that our approach gave the best result compared to these other filters in terms of some distance measures. But again, distance measures all distance measures don't correlate well with the human visual perception of what is good and what is bad in terms of noise, sharpness, and such. Enhancement of color images. One needs to be careful. Sometimes component-wise enhancement and filtering will work, sometimes it doesn't work. So if you just do what we have done for grayscale on RGB separately, sometimes it may give you good result. If you are happy, fine. Sometimes it messes up color, especially. Quite often the enhancement that is required, I'm not talking about noise removal, but contrast enhancement. Quite often it is only for the intensity component. You don't want to touch color. You will assume that the color sensor has done its job. If not, do the color calibration using that color checker. For that, you must take a picture of that first and keep it for the same lighting condition. And do the color correction separately. Noise, do the noise filtering, one of those methods. Preferably using the color angle information also. For contrast enhancement, only the intensity component needs to be modified in most cases. Keep the hue and saturation the same. If you want to adjust saturation, do it separately. If you want to make the color more lively or brighter, but it'll be unnatural sometimes. So gamma correction, histogram equalization, there are two methods we have seen, can be applied to the intensity component. Saturation may need to be increased if you want it to be more lively and more sometimes glaring. You normally don't alter the hue component unless you want to do something very specific. Not typically, perhaps not for natural images. RGB separate analysis is not usually recommended. So gamma correction, I took this picture in Brazil. It doesn't matter where. There is the restaurant there and a nice mango tree here with the fruit hanging there. But I took it this way and there is so much background light. The mangoes here don't show up in the natural color. They're almost black because there is no light going this way. So we want to enhance the color here and perhaps the contrast. And gamma correction applied to intensity only with gamma equal to 0.4. This is enough. The color, you can see the mangoes, they're just intensity correction. Oh, you can see the green here. The rest of the color, they are natural colors. I didn't touch color. Okay. See intensity and saturation enhanced with gamma equal to 0.4. Green is green, okay, but that color is different. The grass is, I don't think you have grass in fluorescent green like that. So that is unnatural color. All the three RGB components enhanced individually with gamma equal to 0.4, not bad. You can see some of the details inside this restaurant that you cannot see there. And also here you can see some if you zoom in, because that's dark compared to the outside sky. And also look at the sky color. You may see sky like that sometimes, but that's not what it was there. That perhaps is the true color of the sky there. This is not bad, but that should be the best using the considerations we have discussed. To enhance contrast, we can use a definition of contrast like this: PR minus PN over PN, like F minus B over B. We have seen the region of interest and its background, and that is grayscale contrast. Or you can use this, PR minus PN over PR plus PN. You can use a circular region. You can use 3 by 3. You can say, this is my region of interest. My reference is somewhere else in the image. Something. You need some reference for the denominator. Grayscale is not a problem. How do you define color contrast? Well, first, the luminance contrast is LMN minus LM over delta L max. I'll give the reference to this paper. This is not our method. So luminance, the color difference was computed in the LAB space, or L star, A star, B star. I just say LAB. So take the Euclidean distance between the two values, foreground, background. The average, the foreground average of the background, the L1 and L2, A1, A2, B1, B2. So you're taking the same Euclidean distance, but now in the LAB space, and that is supposed to be closer to the human visual perception in terms of differentiating between colors. And then CC, color contrast, is CDM over CD max over the entire image. M is the mean over 5 by 5 region. So this is color contrast, just Euclidean distance. And then the enhancement is defined in terms of a certain gain for the luminance and a certain gain for the color for every pixel. And that luminance gain is given in terms of these quantities, delta CMN, which is this difference CLCC, that difference from CLCC from there, and min and max of those. GC is delta C max minus delta CMN divided by the min and max of those. So two separate contrast measures and two separate gains using all these gradients. And then the enhanced value is given by LM plus this factor CE times delta L max if LMN is greater than that LM, otherwise subtract. This is similar to the contrast enhancement I had described earlier. So K is this ratio of LE to L, and the red component is multiplied with KMN, and the same for green and blue. So eventually the multiplication of this factor is done separately, channel by channel, RGB. But they are computed using both color and luminance contrast. So both are enhanced using all of these differences and gradient measures computed and contrast measures, simultaneous contrast measures. You can call this also simultaneous because you're comparing two values. So this was based on a paper by Liu and Yan. I implemented that and got quite good results. I took this picture of a pagoda in Japan, and because I was taking a picture this way and the sunlight is coming from above, the details here are not seen. There's no light going this way. So that's the luminance contrast, and this is the color contrast. So color contrast exists in pixels other than luminance contrast. There's color contrast here. That's a different color. Not so much there. And this is after enhancement. Of course, you can enhance what is there. If it is not there in the original, if it is black, it will be black. So that's the original. You can see some things there. Something has to be there. You can't just create it by magic. But now it is much better. All the color comes up. Okay? Mihai Ciuc from Romania with Professor Buzuloiu, we did this work and published this many years ago, 25 years ago, in the Journal of Electronic Imaging. Color histogram equalization, there are a few different methods. The histogram of a color image is a 3D entity. And based on that, some have said equalize in 3D, equalize RGB separately, and there are many other algorithms. And we wanted to try our adaptive neighborhood paradigm for everything. As I said, when you have a hammer, all problems look like a nail, you want to bang it. But there is some reasoning, as I said. Here we said, okay, we don't want to blow up all colors over the entire gamut. That ruins things. And in most cases, only intensity is to be modified. Color we keep. We will assume that the colors are good, have been captured properly. We don't want to create artificial colors or colors that don't exist in the original. So we brought our adaptive neighborhood histogram equalization technique, put some more conditions to make that method work better with color images. So here is a picture from one of the, again, there are some databases and journals expect you to show your results with all of them. For color printing, it was expensive. They wanted $1,000 per page of color, $1,000. And we had 10 pages. And they said, well, put 5 more test images. We said, well, who's going to pay for that? But anyway, we did that, and I had to go and ask the president's office, go with a begging bowl and ask for money, which they gave me. So this is the original image, and what histogram equalization of each RGB separately. This mountain has become purple, and the green is okay. That part is okay, but this purple perhaps doesn't exist. And some colors here are not present in the original. C is 3D histogram equalization, not so good. Histogram decimation is another technique. All these magenta color pixels have come up. E is histogram explosion. Again, other colors have popped up. This is our technique with some parameters for the number of pixels and some other region growing parameters. So we made some measures and said, well, we're not introducing any other color. Has contrast improved? So we showed some measures, and the main thing was not to bring in other arbitrary colors. Segmentation of color images. As I mentioned earlier, we have the 3D histogram in RGB, and you can define a block. So much of R, so much of G, so much of B, but it's very difficult. I cannot conceptualize or visualize how much of green and red and blue I should put to get this color or that color. Perhaps some of you can do that. But it will be perhaps easier in this plane, hue and saturation, right? And by looking at this, we know where various colors lie. I cannot visualize it here. Perhaps with experience, looking at the 3D histogram I showed for the parrot and others, you can do that. And artists do that. They simply take this color and this color, mix it, and they do that. So it depends upon your experience and how you can imagine these colors. But to me, I can say yellows are there, and brown is there, and red and pink are here, green. It's easier, more intuitive. So put a limit on saturation, which is the radius, and put a limit on the hue, which is the angular range, like a sector filter. We have seen sector filters in the frequency domain for directional filtering. Now direction relates to hue. So segmented green and cyan and yellow. I gave the same range for all of them. And yellow included some of these greens that are, I gave perhaps too broad a range for each one of them. I think I gave 30 degrees. Yellow doesn't span 30 degrees. It's a very narrow range, yellow. So I could have used 10 degrees, and perhaps I would have had only yellow and not those. And last one is black. There is some black there. I can get the white also. I showed earlier how to get the non-chromatic or achromatic parts of the image. So image segmentation into colored parts can be done this way. Now, depending on the threshold you put on saturation, you may get only the pure saturated colors or lighter shades of that color too. So this is the sector filter. If you go all the way down here, you will get all the colors of different saturation in that band. You can make the band as narrow or as wide as you want it to be. So another image alert. If you don't like this image, look the other way. Oh, red there. So this is an image of a skin ulcer in collaboration with Dr. Paulo Mazzoncini in Brazil and his colleagues, a dermatologist. Diabetes causes certain problems, and the veins don't work properly in the leg, and blood circulation is impeded by venous deficiency. There are some different names for that. And then blood circulation is affected and wounds don't heal, and ulcers could be caused by this stagnant blood, and there could be lesions of this kind. They are treated, of course, and the response to treatment is what is important. You want to know what is the tissue composition, like we saw the Gaussian mixture modeling of breast tissue or neuroblastoma tumors. So what is the composition of this, and how is it changing with respect to treatment? So even the initial treatment depends upon the composition. So here, the 3D histogram is shown here. Now, there are some standard protocols. There is the blue sheet always in the background, and there is a color calibration strip. I don't know why they put it on the patient's foot. It could have been kept somewhere else, but anyway, that's what they did. And here you have the pure RGB and CMYK patches. So you can calibrate the image. We didn't do the calibration. but it is possible. This is like those color checker big matrix I showed. This is something like that. So this is the color histogram, including the blue background and everything. Hue saturation histogram. Red is here, yellow is there, and so on. And blue is, there is a large number of pixels here from the background cloth. So segmentation of red, what is called the granulation tissue, saturation more than 0.4, and hue 300 degrees to 0 to 30 degrees. So we put a 60-degree band there, and that's what we get. Now there are some parts here that have passed because saturation is 0.4. This is not red, it is sort of brown, but it has some red. If I had used a different saturation level, perhaps that wouldn't have come up, but then it is possible then to lose some of the lesion part. Yellow is called fibrin. I went with a lower saturation, 0.2, 30 to 90 degrees. It could be made narrower. Yellow doesn't go that far. But that is, the yellow patch also has come. The red and pink patches are here from this calibration patch. Black is necrotic scar. There isn't much, maybe only that little bit. So the model used here in the analysis of skin ulcers is what is called RYK. So how much is red, how much is yellow, how much is black? Black is scar, means it is healing. Yellow is not good. You want red and black. So depending on how much yellow is there, the treatment could be different, how much red is there. And you could follow treatment, the response of the lesion to treatment. So then you can label this as the ulcer region by putting these three components together. How big is the ulcer? Get the area, relative area of red and yellow and black. Okay, so it's not Gaussian mixture, it's actually pixel by pixel. We didn't plot the distribution and so on. We did a little bit of investigation of this and then passed it to the group of the dermatologists, and they did some more work later, and we also computed color texture. Gray level co-occurrence, in the gray level range, you count how many times 0, 0, 0, 1, 0, 2 have occurred, and 1, 1, 1, 2, and all that. You saw the gray level co-occurrence matrix. Now you can do red, red, blue, blue, green, green, like gray level, and then you can do red, green, green, blue, blue, red. You can do all of those. If you want, you can do RGB co-occurrence, but you may not get that many counts of RGB. So it may be better to do RR, GG, BB, and then RG, GB, RB, and that should be enough. And then you can compute all those statistics of Haralick and others. And we have done some work on that. I won't go into that now. So segmentation, just a few more minutes, 7 more pages, I think. I thought I had 53. How many do I have? 53. I'm almost there at the end. Segmentation, the K-means algorithm is a pattern classification algorithm that can be used for color segmentation too. We have a color feature vector here for each pixel, RGB or LAB, whatever. Whichever color coordinate system you use, it's a vector. So you want to ask, does this pixel belong to this category or this color reference, whatever the reference prototype is. So we have a pixel data set, x1, x2, each one of them a vector in R3. Now I'm talking of like our colleagues, R3, R2, and all that. I usually don't use this. I say in the 3D space of RGB, but in the R3 space, V is a code book of centroids for the how many ever regions you want the output to be, to represent. V1 to Vk. And this is a set of pixels corresponding to Vi, x belonging to this capital X, such that the argument of this is given minimum of x minus Vj square. That is, compare each one to each one of these and take the minimum. And that is the class. So starting from a finite data set X, iteratively move the K code vector so as to minimize an error measure and recalculate the sets. That is, you have said you want so many classes, and you started with some initialization of the means of those, the centroids of those, some arbitrary values, or you can select some of the RGB values from the image and say initialize to those. There is the error, X minus VI modulus, and summed over all the categories and all the pixels belonging to those categories, and compute the new centroid, or K means the mean of that category, the ith category. And then keep iterating until there is no more change in the assignment of pixels to categories, or the centroids don't move anymore. So here we have an original image with lots of colors, and the results of K-means clustering in 3 different color spaces: sRGB, S is the standardized RGB, this is HSV, similar to HSI. The intensity and values, the name itself is value. Okay, the intensity I component and V component are obtained in using different combinations of RGB. So HSI and HSV are similar, but the third component, intensity component, is computed differently, and LAB. The image has been segmented into 6 regions, and the color assigned to each region is the final centroid of the color values in the corresponding region in the original image after application of the K-means. I found it very difficult to understand or interpret these images in many papers. They may not describe what is this final color. So this color means that flower has been segmented, and that is the average color of that population of pixels. See, there is some black, light, how should I say? It's pure yellow there, but there is some other color there. So when you average, that's what you get. But the color is different here. The color is different there. Even this is different, of course. But the segmentation, perhaps, where can I show some difference? This rose has red and yellow, but in this method, that whole area has been put together, resulting in this some brownish color. This is what? HSV. Here, the red and yellow parts of the rose have been identified separately, and this yellow flower has been segmented differently. This is not bad. The yellow parts are there. So like that, you compare each one, and this is supposed to be the best. That may not be so bad after all. So you look at that and make your own analysis, but compare each region with the corresponding region. This has averaged out this whole flower with all the white and pink. They're all put together. Here you can see the pink and red and white separately. Okay. So depending on the space that you use, I think the observation is that depending on the color representation space that you use, RGB, sRGB, XYZ, or LAB, LUB, you may get different results. Which one is the best? You analyze and check, and LAB, LUB are supposed to be the best in terms of agreement with the human visual system. That's how they were developed. So the peppers image, they all look good, but that area the dark area here has been identified separately in the LAB. This has averaged out. There's an interesting paper with a biomedical application in histopathology. I'll give the author's name later. This is not our work. Called color deconvolution. In histopathology, multiple stains are typically applied to the same tissue sample in some process. I don't know the sequence of application, but that's what they do. There is hematoxylin, eosin, and DAB combination in this case. In terms of RGB, these are the colors of those stains. So there is this vector P that represents the 3 stains. And then a pixel in the color image of that tissue, every part of the tissue will take up a combination of this. Some will take more of hematoxylin, some will take more of the eosin, and so on. But there'll be some mix. So a pixel Pij, the mean is computed. Pij, it's normalized rather, Pij over this sum of the squares, square root. The color pixel RGB, it's not the whole image, but 1 pixel. Y is Cm. It's like a mixture model. And then you want to get the actual color, Y M inverse. M is the normalized matrix of the RGB values for the dyes. That is, this is normalized. C is Ym inverse. You want to invert the effect of that. So this is what was done by Ruifrock and Johnston in their paper. So this is the original breast biopsy specimen stain with a combination of hematoxylin, which is blue, eosin, which is magenta, and DAB, which is that brown. And they wanted to separate them. So each pixel has a combination of these, and by inverting, these are the color definitions in RGB of the stains. Normalize each value here, Pij, with this, and that gives you the matrix M of this stain. So a pixel in the given image is Y equal to Cm, and you want C, which is Ym inverse. M is only 3 by 3, so inverting that should not be a problem. So on a pixel by pixel, you separate into the blue, the magenta, and the brown parts. So they can see now, you can see how the stains have been distributed, which parts have taken more of a particular stain when the tissue specimen has been stained with multiple dyes. They call this color deconvolution, which is a very interesting thing. Not image deconvolution, but color. So that is what we have in the book, a quick overview of the book and a few important concepts and some applications, some algorithms. All the color filters, there are so many noise filters, they're all described in the book or in some of our papers. There are a number of other topics: edge detection, region growing, morphological image processing, hyperspectral imaging, analysis of texture, coding, data compression. We did some work. Analysis applications, analysis of burn wounds that Carmen and Begonia have done, skin ulcers that my colleagues in Brazil have done, teledermatology that Carmen and Begonia are doing and have done, telepathology, hyperspectral aerial photogrammetry with LiDAR. That's a big thing. In Calgary, there are some companies, one of my grad students worked for a company doing this, aerial photogrammetry, using hundreds of bands, very narrow bands. So the natural light is broken into 100, 200, 1,000 bands. So each pixel is having 100 to 1,000 values, not 3. So how do you analyze those? You want to separate into various types: building and road and rail and agricultural land and snow and this and that. So that can be done. But then you have to deal with vectors that are much, much bigger. So now instead of calling it color image processing, you can call vectorial image processing. Vector of any size. And the vector could also be multimodal images in medical imaging, CT, MR, ultrasound, whatever. But registration to the same size and geometric mapping will be a problem. That can be done. There are techniques for that. Then you can make one vector for each pixel with all these data. You don't have to display, you analyze them. Vectorial image processing perhaps is a better and generic terminology for this. I missed something. There is another topic, that is, how do you apply transforms? How do you take the Fourier transform for color image? How do you find correlation? So there are some relatively new methods for that. And Jose, who is a colleague of Carbon and Begonia, he's our fourth co-author on this book, the second edition. We are trying to bring in some of these topics, and we have finished 3 chapters, I think, out of 8. So it'll take some more time. We'll expand the book and come up with more illustrations of techniques and applications. So thank you for your attention, and are there any questions about this? Any comments? Easy.
Color can be a good feature.
Yeah. For classification of
Objects.
yes. The problem will be, the reason I put up that collage of so many pictures with the Kathakali dancer and so on, electric wires. When you take a color picture of some scene, you don't know what that color is. This is natural color, but this fabric could be of any color. That color has no meaning there. Even this color has no meaning, but you have to identify the person, for example, and if it is color coded, different types of wires, what is R and what is G and so on. So interpretation of the color in a real life scene would require knowledge about whether it is natural color or simply some paint applied, or is it fabric, some textile, and if it is color on a computer chip, if it is color coding of telecommunication wires, you must have seen all those wires. I have a picture of that going into the computer, and your communication wire channels, they're all color coded. The color may mean something or not. It could be just random, just put this color into that color there when you connect. But a color image could be interpreted, and there are cultural connotations. We have our national flag. The colors mean something. Each color in every flag has been put there to represent some philosophical aspect. So then interpretation of color is a more difficult question. Segmentation, just pixel-based, image-based operations are okay. If you're asked to interpret, then there are many, many other issues that come up. Natural color, pseudo color, color coding, staining. And
true color. What is true color?
True color, this is my true color. Yeah, I didn't put any makeup, so this is my true color. And if you look at my retina, that's the true color. And if you cut, what you see is my true color, right? So, yeah, those are true colors. This is nothing. Some objects have the inherent color property, like the green leaves and brown bark or whatever of trees and the patches on animals, those. But then the perceived color is dependent upon the illumination. So true color is what is there on the object. But your captured color depends on the illumination and your detector. And that has to be calibrated if you want accurate depiction or recognition of that color.